Welcome to Lesson 5 on molecular polarity. Our lesson objectives determine the polarity of a molecule and determine the shape of a molecule. In looking at a molecule, there are two types of electron pairs. We have the bonded pairs, which form bonds, as in the case of the bonded pair of electrons between the hydrogen and nitrogen. So there are three bonded pairs here. And then there's the unbonded pairs that are not involved in bonding. We call those the lone pair electrons, as in the case of this pair here. The polarity of the molecule, now we've learned about bond polarity, which is the difference in electronegativity between two atoms in the sharing of electrons. That was in lesson 2. Molecular polarity is the polarity of the whole resulting molecule. And that depends on bond polarity as well as the shape of the molecule, whether it's symmetrical or not symmetrical, as we say asymmetrical. And the resulting shapes of the molecules is caused by something called VSEPR, which stands for the valence shell electron pair repulsion. What this basically means is that electrons are negatively charged and they will repel each other because like charges repel like charges. And so these electrons are going to push away from each other, and as they do that, the molecule is going to change its shape. And it's going to arrange itself where the electrons are as far away from each other as possible to help minimize that repulsive force. So in the case here for H2S, you can see that the bonded pair, represented by the lines here, they're repelling each other in both directions, this way as well as this way. And so are the lone pair electrons. They're repelling each other in both directions. And so this molecule then forms this linear type shape and not maybe a bent shape because the electrons are repelling each other in both directions. And so what we get is something either called a polar molecule or a nonpolar molecule. So polar molecules contain polar bonds, and in terms of the shape, they are asymmetrical, not symmetrical, and so they have a asymmetrical distribution of charge. So in the case of HCl here, chlorine is much more electronegative than hydrogen, and so this is a polar bond here, the sharing of electrons. So the electrons are closer to chlorine, as we've learned, and it develops a partial negative charge, and therefore hydrogen develops a partial positive charge. Because this molecule is not symmetrical, it's not the same type of atom on both sides, the electrons, or the distribution of charge, is towards the chlorine side, and so it becomes a polar molecule. We have a negative end and then a positive end of this molecule. Same for the case of water here in this bent molecule. A key note really to help you out is if you ever see lone pair electrons, so here we have two lone pair electrons on the central atom, that automatically makes it polar. So what's going to happen is these electrons are negative and they're repelling each other, and they're going to make this molecule kind of bend. And what happens is now the oxygen, which is much more electronegative, develops a partial negative charge. And because of this bent shape now, it's asymmetrical. It's not the same on all sides. We have hydrogens on this side and we have lone pairs on this side. Then we have, I can kind of draw a dividing line here. We have a negative end of the molecule by the oxygen and positive ends by the hydrogen. A molecule then is nonpolar if it contains nonpolar bonds only, or if it is symmetrical in terms of the distribution of charge. As in the case here for carbon dioxide. You can see it is symmetrical. It's the same on both sides. And so there is no net distribution of charge where I can't say there's a positive end or a negative end of the molecule. So let's first look at the shapes of polar molecules, and then we'll look at nonpolar second. Linear is pretty straightforward. It's a straight line in terms of the shape of the molecule, and linear could be either polar or nonpolar. So for a polar molecule, for it to be linear, it must be asymmetrical. As you can see here, I have a carbon on one side and I have an oxygen on the other. This is asymmetrical, not the same on both sides. If you look at the bond polarity, the electronegativity difference, oxygen is much more electronegative, and so the electrons are being pulled to the oxygen side. Because this molecule is not symmetrical, then this whole side of the molecule, as you can see in the arrow, the electrons are being pulled this way. This whole side of the molecule is negative, and this side is positive. And so it becomes polarized. And so this is a polar molecule. Next polar molecule is the bent shape. And it's named after the fact that the molecule is no longer linear, it's kind of bent. It's also asymmetrical because I have hydrogens on this side and lone pairs on this side. Notice that it has lone pair electrons, and I mentioned earlier, if you ever see those, it's automatically polar. But here's why. Oxygen's more electronegative, and so the electrons are being pulled closer to the oxygen side. Because the molecule is not symmetrical, I can kind of run a clear line down the molecule here and say that the hydrogen side is the positive side, and this oxygen side of the molecule is the negative side. You can see it even more clearly here in this 3D rendition here. So the oxygen side of the molecule here is the negative side, and the hydrogen side over here is the positive side. And this actually which allowed for me to move that stream of water with the static electricity because of this asymmetrical distribution of charge, and that there was a positive side and a negative side of the molecule. And the last shape for polar molecules is the pyramidal or pyramidal. And notice that there is a lone pair of electrons on the central atom, which automatically makes it polar, as I mentioned earlier. Because it's hard to see in this model that distribution of charge. But you can see that it's not symmetrical. I have hydrogens on three sides, and then I have a lone pair on this side. But if you look at the 3D model here, you can see a little bit more clearly that the nitrogen, which is more electronegative, this side of the molecule is the negative side, and then down here is the hydrogen side of the molecule, and that's the positive side. So let's check your understanding. Can you determine the polarity of a molecule, and can you determine the shape of a molecule? Now let's look at the shapes of nonpolar molecules. For a molecule to be linear and nonpolar, it must be symmetrical. So, as in the case for oxygen or carbon dioxide, you can see it's the same on both sides here, and for carbon dioxide, it's a mirror image, or the same on both sides. So they're both symmetrical. In this case here, it's a nonpolar bond, and so there is no distribution of charge. It is the same. They're pulling on electrons equally, and so there's no negative or positive side, and this is a nonpolar molecule. For the case of carbon and oxygen, even though oxygen is more electronegative and the electrons are being pulled slightly towards the oxygen, they're being pulled in both directions. So due to that set symmetrical distribution of charge where the electrons are being pulled to the right side and left side of the molecule, there's no overall positive and negative side, and therefore this is a nonpolar molecule. And the last shape we have is the tetrahedral, which is always nonpolar. We have a central atom, and then we have tetra, meaning four identical atoms around that central atom. And the most common example we'll see in this course is methane, CH4. In this case, these bonds are all nonpolar, so the molecule is nonpolar. But even if the bonds were polar and the electrons were being pulled, let's say, out towards these bonded atoms, because it's symmetrical, the charge is distributed symmetrically, and there's no overall negative side or positive side of the molecule. And so therefore it is nonpolar. So here's a summary of the shapes and their polarity for you to reference as you're working on your practice problems. And let's look at a few examples. So we want to determine the polarity and shape of CCl4. So the first thing you have to do is actually draw out the structure. So I'm going to draw my central atom, and then I draw in my chlorines around it. I assign my valence electrons as we did in our previous video on Lewis dot diagrams. And you'll see that it is 4 atoms around a central atom. And so the shape is going to be the tetrahedral, and the tetrahedral shape is always nonpolar. Even though the chlorine atoms are much more electronegative, the electrons are being pulled in all directions equally, and so the charge is being distributed symmetrically, and therefore it's a nonpolar molecule. There's no negative end or positive end of this molecule. Last example, determine the molecular polarity and shape of H2S. So when we draw out H2S, we see that it forms this bent shape. I see that it has lone pair electrons on the central atom, which automatically makes it polar. And because it's kind of bending, it forms this bent shape, much like water. Let's check your understanding. Can you determine the polarity of a molecule and determine the shape of a molecule? At this point, you should be able to determine the polarity of a molecule and determine the shape of a molecule.